In this video, we will convert a chain rule into code for automatic differentiation, a simpler version of what's found deep inside many of the big machine learning frameworks. There are many machine learning frameworks out there that make it easier to build neural networks. Many frameworks provide features like layers, loss functions, optimizers, training loops, and some even help you deploying your neural network model. But there is one feature that is seldom mentioned. It is the most fundamental and might even be the most important feature of them all. Building a modern neural network without automatic differentiation is practically out of the question. When training the neural network, it tells us for each variable how it should be modified in order to get the desired output. Auto-differentiation might sound magical, at best something that is hard to implement. That is probably right, but creating a basic version is actually not that difficult. We will not be using it for neural networks, but we can use it to solve those pesky equations from math classes. Join me in coding a version of auto-differentiation. We will literally rewrite the chain rule to mathematical and programmatic magic. First, we'll code the plain derivative. Then, we'll rewrite it to auto-differentiation. Next, we'll use it to solve an equation. And finally, we'll summarize and talk about the implementation. Let's start by creating the main class. And now, let us look at the definition. This is the chain rule for two independent variables, a and b. First, the main calculation. A and b are first given as inputs to two different functions. The output values are stored as x and y. They are then given as inputs to a third function, and thereby getting the final output z. The final and fun part is the partial derivatives of the main calculation. This might look complicated. It's actually kind of like a mathematical chihuahua. At first glance, it looks like we multiply together fractions of many unknown values combined with a scary looking symbol. But in reality, they're just a handful of values combined by 4 multiplications and 2 additions. In our code, each of these fractions are just different variables, so 5 in total for the first row. And the first definition here is read like this. The partial derivative of z with respect to a. For me, this means how much the value a affects the value z. We'll have a close look at this later, so don't think too much about it. As promised, we'll rewrite this chain rule, so let us copy it. Let us create a main method to work with and paste the definition here. We'll start by calculating the main result z. This is the plain calculation, no derivatives yet. To make this easier, instead of 3 different functions, we'll just use the same one. We'll use a multiplication. Oh, spoiler alert! Since we know that this algorithm will involve some recursion, we need to encapsulate the values in objects. This makes it easier to work with. Now we take A and B as inputs and convert them to node objects. Then we pass them to the multiplication function. We do the same with x and y to get the final output z, which we then return to the caller. Now we need to execute this code. We'll be using a testing framework, but we won't be doing any test-driven development. It's mostly because it's a convenient way to run and check out code. Let's create the test class. Here, we simply call our calculate function with a as 5 and b as 3. Let's run it. Okay, we got our output. Now we can do the fun part, the partial derivatives. First, let us clean up this definition. There are some multiplication characters missing from the copy and paste. Let me pull up the definition. As you can see, there should be multiplication here, 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 and here. Let's go back to the code. This is better. Now it matches the definition. Let us convert this to code. As mentioned earlier, this means the partial derivative of z with respect to a. Let's rename all these variables. We'll call this the partial derivative of, and replace this character with respect to. That was easy. Now we need to find the values of these missing variables. We'll start with this one. First, let's take a note of the source calculation for this specific partial derivative value. X equals to a multiplied by b. In order to find the partial derivative of x with respect to a, we'll treat all other variables except for a as constants. That means we'll treat b as a constant. Let us create a hypothetical equation where b is a constant. For example, x equals a multiplied by 5, which can be rewritten as x equal to 5a. We know that the derivative of this is 5. In other words, it's b. We assign this variable to the value of b. Let's do the same for all the other variables. That's it for the derivatives of a and b. We just return them together with the result. And the result class now includes these values and can also display them when needed. Let's run it. We now got the partial derivatives of z with respect to both a and b, which is sometimes called the gradient. But how do we know that this is correct? Let us imagine that we have this magical estimation that we can test against. Here we have the magical estimate of the gradient with values for both a and b. These values are then tested against what we calculated within some margin of error. What we'll now implement is something called numerical estimation. What is this numerical estimation? We'll have to consider each input variable separately. Let's take a as an example. Let's say that the input value a is here. and the final output z becomes this. What we'll do is nudging a edit. Let us add a small distance to a. We will call it h, and let us just say that the output of this nudged a becomes a bit higher. What we then need to do is to find this slope, and given these names, the estimate for slope is calculated like this. We'll implement a slight variation of this, which often gives us better estimate. We simply center h on a like this. Let us suppose that the output follows this curve. The real derivative slope will be something like this, and the centered estimate should be something like this. The centered estimate is more accurate than our first estimate. Let us implement this. We'll start with a's estimate. We will only nudge the value of a. Then do the same for b. Here we estimate the gradient for a numerically. The gradient value for b is calculated below. Both values are returned from this method. The estimate class simply stores the values and can display them when needed. Now let us run this code. We should print the estimate. And now let's see if the estimates are close to what we've calculated in our main code. Yes, not bad. It feels good to know that our main code is correct. More than that, we will now be notified of any bugs that crop up in our main code. Numerical differentiation is powerful in that it doesn't care what the main calculation does, it just works. And the downside is, of course, it's not that accurate, and we need to run the calculation twice for each value, but it's perfect for testing our implementation. Phew, we've now finished the first part. Next, we will rewrite this to auto differentiation. We know that this algorithm has to work with the node objects, either in a loop or by recursion. Either way, there is two main tasks that we need to do with this code that calculates the derivative. First, we need to move all the values into these nodes. And second, the calculations here need to be loop or recursion friendly. By that, I mean they need to have a common form. Let us start. First, let us think about what this partial derivative of z with respect to a means. It means how much a affects the variable z. Since z is the last and final output node, let us assign this as the gradient value for node a, and likewise set this one as the gradient value for node b. There. Now we can just return those two nodes. There, not much has changed, we just changed where we store the gradient. But just in case, let us test this. Good. Now I just split the single line into 2 lines, and I accumulate the values. The result is still the same, as we can see. Okay, the test still passes. Now, let us put these values into the nodes. If we look at this variable, we know that y is created by applying operations on a and b. So, y itself should know about its own partial derivatives with respect to all its inputs. And that's the same story for all these variables. Let us put these values into the node itself. Okay, the logic is still the same, we've just changed where the values are stored and read. In this line, we put the partial derivative of x with respect to a into the partial derivative with respect to map of x, and that same value can be read from this map by using a as the key. The logic is still the same. Let's just run a test to double check. Good. Here we just assign the gradient of only a and b. As with any iterative or recursive algorithm, the same should happen to all the nodes. Let us try assigning the gradient for all the nodes. Let's start with x. But what should it be? Let us draw the calculation graph to make it easier. If gradient A means how much A affects Z, but then wouldn't gradient of X mean how much X affects Z? And that's also called the partial derivative of Z with respect to X. I swear that I've seen it. Let us find it. So that means the partial derivative of z with respect to x. It's this one. Let us assign it as the gradient. And it's the same story for the gradient of y. And then the last node. The gradient of z must mean how much it affects itself. I don't know if this makes sense, but in my mind it's like taking the derivative of this equation, and the derivative of this variable is 1. We can see that these two lines does not have the same form. Let's fix it. Actually, let us talk a bit about the calculation. Let us draw out the calculation graph. Our calculation looks something like this. We have two inputs, A and B, which are then used to produce the node X and node Y, like this. And finally, we have the Z node. And whenever you have an algorithm that works with nodes, it is much easier if the algorithm only needs to read from the current node and its nearest neighbors. What I mean is, for example, in this code, the gradient of A is calculated also by some value from Z. And if we look at this graph, A's nearest neighbors is only X and Y. It should not know anything about Z. Let us try and fix this. But now, if you look closely, we have duplication of code. Let me highlight them. And since we don't want Z to be referred to by calculation of a's gradient, we can just replace this with the gradient of x. We can do the same thing with the gradient of y. We can see that these two lines does not have the same form. Let us do the accumulation of the gradient in these lines. If we now look at this pattern, you can see that we multiply the gradient of x by something from x, and the same here, the gradient of y multiplied by something from y, and same thing here, x with x and y with y. So that means we should have the gradient of z here. And since the gradient of z is 1, that shouldn't change anything. And if we look here, we read from z. That looks okay. Here we first read from x, and then from y, and same here. That doesn't feel right. Let us look at the calculation graph again. What we want is for the logic to start at z, then go down to x, and from there go to a, and since a does not have any nodes below it, x will then go to b, and then z can continue to y. But what's important is that x must be finished with both a and b before y is allowed to be read. We need to fix this switching between x and y, and then x and y again. I've just moved those two lines, and since we accumulate the values, the execution order of these lines does not matter. And now this looks much better. Let us just test that we have not broken anything. Good. Let us take a closer look at these lines. You might spot a pattern there. First, you might spot that both x and y are keys in this partial derivative with respect to map. Obviously, since they can be used to get values out of it. And that means that we can get both these nodes x and y from this map from z. And here we are referring to the same node, z, and it's the same pattern for both these two sections. Let us convert this to loops. Now, that loop should do the same thing as these two lines. Let's comment these out and run the test. Now we can do the same loop for both x and y. There, let us run the test again. Minor cleanup. Since we have 3 logically identical for loops, we can extract a method from them. The editor suggests that we can replace this code with the extracted method. Let us let it do its magic. There, let's run the test. Since we want to keep everything in the node, let us move this method into the nodes itself. There, let us run the test again. Notice that both x and y are dependencies of z. So instead of calling this method here, we can let z call them on its own dependencies. Now we let each node call this push gradient to dependencies method on its own dependencies. And that means we won't be needing these lines anymore. Let's run the test. If you look at this section, you'll notice that for x, we are only referring to the input values. And that kind of makes sense, because the partial derivative of any output value with respect to its input would be some combination of its inputs. And that means we can move this code into the multiplication method where x is created. There, I moved the assignment of a and b's value into this method. And that means we won't be needing all these put calls anymore. Let's run the test. Now, we're almost finished. Let us add some additional operations. There, we've now added addition and a square function and subtract. Here we use the auto differentiation itself to figure out the derivative. And here we have negate, and that should be about it. Let us just modify this equation. For example, let's add a to this and run the test. It's still correct, but how about now? Let us add x to the calculation of y. Let us run the test again. Oh no, the gradients does not match. Our gradient of a is higher than the estimate. Something is wrong. But do not despair. We'll fix this. Let us look at this code together with a calculation graph. Let's highlight the temporary nodes. These two multiplication calls also return output nodes, but they go directly into the add function. We will draw those nodes in their respective colors. This graph is read like this. Take the z node as an example. Z is created by reading from both x and y, and that's shown in this graph where z points to x and y, and x is created by reading from the temporary node that is returned by the multiplication and the a node, and that's what we see here in the graph. X is created by reading from this temporary node and a. We will use this graph to see how the code traverses each of these nodes. Let us go back to the push gradient to dependencies code. Let us concentrate on just this method. Imagine that we start the gradient calculating process by calling push gradient to dependencies on the z node. We will then loop through these dependencies. Let's say that the first dependency is x. This node will then be the x node, and this value will be the partial derivative with respect to x. Z will then multiply its own gradient with the partial derivative with respect to x, which is then accumulated into x's gradient. It will then call the push gradient method on x. Let us take note that the gradient of x already have some value. Let's say that the gradient has been added by this amount. It was done here, and it was from z. And the same thing will happen from x to a, and then from x to this temporary node, and again down to a, and then down to b. But now there are no more nodes to process on this section of the graph, so the code will go back up to z. Now z will continue down to y, and then y to x, and what happens now is that y will also add some amount to the gradient of x. X will then add an amount to a's gradient. But that's where we get this inconvenient feature. This is the amount pushed to a. Note that x will use its total gradient value. That means all of this. But x has already pushed this amount to its dependencies. It has now been pushed twice. Let's fix this. Let me add this keyword to the gradient. It has no practical function in this particular piece of code. I only want to emphasize that the gradient belongs to this or the current node that is executing the code. Okay, it's always tricky to fix bugs in recursive methods. We kinda have this chicken and egg problem. By the way, the egg came first. We only want to push the local gradient. Let us start by calling this the local gradient, and then we want to push only that value. And here we receive the local gradient of the parent. That is the node that pushed its local gradient to us. And here we don't want to read the total gradient, but only what's been pushed to us. There. Let's run the test. Oops, of course, we need the local gradient for the initial call also, but what should it be? Let us look at the code again. If you look at this pattern, we have a variable added to the dependencies gradient, and then we push the same variable to the dependency, and if we go back, that same value is this one, so we just use it. Now let us try run the test. Success, but we're not done yet. Look at these two lines. It is peculiar to add some value to a node, then on the very next line pass that same variable to the same node. Here we should make the dependency node add its own gradient. That means, let's don't forget the initial call. Since z will be accumulating its own gradient itself, we won't be needing this line anymore. Let's run the test again. Still passes. There you have it, our own implementation of auto differentiation. We can now solve an age problem. Adam is 24 years older than Bell, but in 6 years, Adam will be 3 times older than Bell. Question: how old is Adam? We can extract 2 equations from the text. Adam is 24 years older than Bell. And the second one, but in 6 years, Adam will be 3 times older than Bell. To solve this problem, We could do it algebraically, but that's too easy and no fun at all. Instead, we start with random values and then change them in small steps, so the error eventually becomes practically zero. The changes will be guided by the gradient from our auto-differentiation code. Let us copy this text. One strategy for solving this is to calculate a total error. We can then use auto-differentiation to calculate the gradient for each input. The inputs are then modified using the gradient in such a way so the total error becomes near zero. The error of these types of equations is, for example, the left side minus the right side. This error value can be both positive and negative. We want a value that is zero if the left and right sides are equal. If not, then it must be a positive value. We will therefore square the error value. Let's code the corresponding code for the second equation. And finally, we need the total square error. This method will just return the total square error. We now have implemented the equation from the age problem that returns the total square error of the input age values. Next, we need to initialize our starting input values for Adam and Bell. We will also need the so-called training loop. Our simple training loop will calculate the error from the current input values and then modify them according to the gradient. First, we create a new random generator with a fixed seed of 3. It ensures that we get the same sequence of random values each time. Then we assign random values to both the Adam and Bell values. Here we have a for loop that runs 1000 times. This creates node objects from our input values, which are then to calculate the error. This triggers the calculation of the gradient, but here we need to modify the input values according to the gradient. But how should the values be modified? Now it's the time to take a closer look at the partial derivative of the total square error with respect to these two variables, which is in our code this gradient field of the node object. It will also be useful to review the code for numerical estimation. Remember that we estimate the gradient by taking the output from the calculation where the input has been added by half h, subtracted by the output of the calculation where the input has been subtracted by half an h, and then divided by h. Now let us look at two different cases for different high and low values. First, let us see what happens when the output increases when we increase the variable. Let's call the variable a. The estimate is calculated by subtracting the low from the high and divide by h. We can see that the estimate is a positive value, since high is higher than low. Now let us look at the other case where the output decreases while a increases. And again, we calculate high minus low divided by h. In this case, we can see that the estimate is negative. It's because high is subtracted by this value that is higher. Now, we need to examine what happens when we add the estimation of the gradient to a. Let's take the positive case first. A is here. The gradient is positive, so adding it means we go to the right. For example here. So by adding the gradient, the error increases. Let's do the second case. And again, A is here. And like our case above, we want to add the gradient. But this time the gradient is negative. And adding something negative means we subtract. And that means we move A to the left. For example here. And as we can see, by adding the gradient here, we also get an increase in error. The conclusion would be then, by adding the gradient, we will increase the error or the output. But we don't want to increase the error. What can we do? Yes, we go the other way. We subtract the gradient. But we don't want to subtract the whole gradient. We only want to subtract a fraction of the gradient. Otherwise, the system becomes unstable and we won't find a solution. We multiply by the so-called learning rate, which is a small number. Let's print out some values. And now let's run it. We can see that the error is a very small number. And it seems like Adam is 30 years old while Belle is 6 years old. It's safe to say that our code worked. Hooray! We started with a chain rule for two variables. It was first converted more or less directly to code, before we rewrote it to a version of automatic differentiation, actually to a version of reverse mode auto differentiation, since the gradient calculation starts from the last result node and runs backwards towards the input. This implementation of auto differentiation is inefficient. For example, it may process a portion of the calculation graph multiple times, depending on the overall connectivity of the graph. Nevertheless, it can be used to solve basic equations with multiple inputs. Another downside with this code is that it only supports scalar values and not tensors, not to mention the inability to use the same variable multiple times within a single operation due to the usage of map as a storage for the local partial derivatives. Maybe you can improve and optimize it, or write a better version altogether. That's the end of our trip for converting a piece of math to a piece of code. If you have any comments, please leave them down below. Thank you for watching. See you in the next video.